started. I'm very happy to have Claude-Andre here. He's going to now say his last name for us.
Faucher-Giguere.
So he's at Northwestern now, been there now for a few years. Almost 4 years, wow, okay, time goes by fast. And he was an Einstein Fellow there, as well as a Miller Fellow at Berkeley. He got his PhD at Harvard, presumably with Lars Hernquist, who many of us, of course, have read papers by his team, and today he'll be talking about his simulations work.
Thank you very much, Lee. So today I want to tell you about work on the regulation of star formation by stellar feedback, including circumstances in which that feedback regulation, in some sense, fails. And so one of the key words in this presentation will be bursty star formation. And I'll cover its implications for a variety of environments ranging from local galactic nuclei to high-redshift galaxies. And one of the concepts that I want to emphasize in this presentation is how the ratio between the local dynamical time in a system and the time scale it takes for stellar feedback to act can, at least to first order, be used to understand the circumstances in which a star formation tends to be time steady versus highly bursty. So the plan of my presentation is to first start with circumstances in which stellar feedback can effectively regulate star formation in galaxies. And I will argue that it provides a compelling explanation for the observed Kennicutt-Schmidt relation. So these are ideas that have actually been around for a few years now in the literature, but I want to repeat them today because understanding when stellar feedback is effective at regulating star formations allowed us to investigate the circumstances in which that model is expected to break down and to instead produce highly bursty star formations. And I will argue that this happens in particular in places in the universe where the local dynamical times are short. This applies to local galactic nuclei as well as at high redshift, in which where I will argue that entire galaxies actually share many properties with local centers of galaxies. And I'll cover several implications of bursty star formation, including for the gusty nature of galactic winds at high redshift and the emergence of well-ordered galaxies at late time, as well as time permitting at the end for what I call the two-phase growth of supermassive black holes. So the pattern in this presentation will be that I'll first give you a very simplified analytic argument, and then I'll follow it up with much more self-consistent numerical simulations that appear to realize the behavior that I would have explained analytically. So if you're not fully convinced by the analytic argument, just be a little bit patient, and then I'll show you the full numerical simulations. Okay, so this is the observed Kennicutt-Schmidt relation. So this is a very famous relation in astronomy between the star formation rate surface density of galaxies. So this is the star formation rate of a galaxy divided by its area, and an analogous quantity, which is the gas surface density in the same galaxies. So you can see that this relationship is observed to be, in my view, remarkably tight. So that alone, I think, demands an explanation. And this relationship is also particularly interesting because observationally its normalization is unexpectedly low. And the sense in which the normalization of this relationship is unexpectedly low is that there is a simplest expectation for what the star formation rate of a galaxy should be. And it is that it should be of order the gas mass in the disk of a galaxy divided by the characteristic freefall time that it should take gravity to pull that gas together and turn it into stars. And very roughly, this gravity-only expectation is shown by the solid red curve here. And what you can see is that observations indicate that real galaxies are turning their gas into stars at a rate which is only 1 to a few % what gravity alone would predict. So we want to understand why star formation in galaxies is so slow in this sense. And so what I'll argue is that this is very likely thanks to the action of stellar feedback. So what we mean by stellar feedback in this field is simply the fact that when a bunch of new stars form, they can return very significant amounts of energy as well as momentum in the interstellar medium. And for galactic scales, the feedback in terms of its energetics tends to be dominated by massive stars, which act in multiple ways, including via the emission of ionizing radiation, which can heat the surrounding gas as well as directly push on it via radiation pressure. Both young and evolved stars also can drive wind from the photospheres that can interact with the ISM. And perhaps the best known form of stellar feedback is a supernovae that you get a few million years after the birth of massive stars. So what is shown on the left-hand side is an active star-forming region in the LMC in which a cluster of young massive stars is driving the expansion of a bubble of dust and gas via the action of these feedback processes. And we now have some quantitative understanding of these processes that are encapsulated in so-called stellar population synthesis models, like Starburst 99 here shown on the right-hand side. So this is an output from Starburst 99, which quantifies the momentum flux that's returned by several of the known main stellar feedback processes as a function of time since the birth of star formation. So we have the momentum flux in radiation in solid black, in stellar winds in dash blue, and in dotted red for supernovae. Now this quantitative plot has a few important features. The first is that to order unity, at least to order magnitude, the momentum flux that you get on these different stellar feedback processes is actually comparable. So this is why in numerical simulations that attempt to in detail capture the effect of stellar feedback, we really should simultaneously include these different processes because all of them are significant in terms of the instantaneous return in momentum per unit time. This is furthermore important because these different processes couple differently with the properties of the ambient ISM and have different time dependencies. And so their interactions with one another can have consequences that would be difficult to accurately anticipate in simplified galactic models. Okay. So this is why the numerical simulations I'll show in this presentation, we have approximations for each one of these stellar feedback processes, including the proper time dependence of them as captured in this particular stellar population synthesis model. Now that said, the horizontal axis here is logarithmic, so and if you take the integral under these curves, you can show that supernova feedback generally dominates the total momentum input in the ISM by about a factor of 5. So this is why for the simplified analytic arguments, I will generally focus on supernova. Okay. So the next thing that I want to do is start with one of these idealized analytic arguments to propose an origin for the observed Kennicutt-Schmidt relation. So this is a simple model in which what we imagine is a galactic disk in a quasi-steady state in which new stars are forming in the gaseous of the galaxy with a star formation rate surface density sigma dot star and a gas surface density sigma in the disk plane. And what happens when new stars form is that after a few million years, supernovae start exploding, and they deposit kinetic energy in the interstellar medium that gets converted in turbulence. And the turbulence provides an effective form of pressure in the interstellar medium. We call that turbulent pressure. And analytically, we can show that this scales linearly, as you would expect, with a star formation rate surface density in the disk. That's with the star formation rate. And importantly, also linearly with this parameter P star over M star, which quantify the strength of stellar feedback. So this is the momentum return in the interstellar medium per unit stellar mass. And for specific feedback processes, like supernovae, this is actually a number that can be calculated from models of supernova remnant evolution and an understanding of the initial foresight. And the basic physical postulate in the model here is that on average, galactic disks are in a state of vertical hydrostatic balance, in which the turbulent pressure in interstellar medium balances the gravitational weight per unit area of the overlying gas. And P grav here is what I call the gravitational pressure, or that weight that I just described. And that scales linearly with Newton's constant, and in the case of a disk which is dominated by its gaseous mass, the square of the gas surface density. And by equating these two expressions, that is by postulating vertical hydrostatic balance, we can derive a very simple prediction for the Kennicutt-Schmidt law, shown in the box orange box here. And you can see that in this simple model, the normalization of the Kennicutt-Schmidt law is set by this ratio, which quantifies the strength of gravity through Newton's constant and the strength of stellar feedback through P star over M star. And so in this model, the normalization of the Kennicutt-Schmidt law is predicted to be low because in this sense, gravity is weak compared to supernova feedback. Okay? And here I should just point out that while this argument is highly simplified, it can and in fact has been generalized to include different physical mechanisms, for example, radiation in addition to supernova, which can be important in low gas surface density galaxies, as well as contribution to the potential that are collisionless, that is stars, or dark matter, in addition to the gaseous component. Now, what I want to do next is actually see how this simple model compares to observations in the limit where it should apply best given the simplifying assumptions that have been made. And this limit is a limit of high gas surface density galaxies on which I have focused the data calculation here. So on this panel, each one of the colored points is a measurement, observational measurement of the Kennicutt-Schmidt law in this regime, and the solid black curve is the model from the previous slide, evaluated for P star over M star appropriate for supernova feedback. So what you can see is that in spite of the simplicity of the model, it does remarkably well at explaining the observed Kennicutt-Schmidt law. In particular, it does remarkably well in explaining in simple terms why this relationship has a normalization which is about a factor of 100 below what gravity alone would predict. That's because for supernova feedback, P star of M star is sufficiently large compared to G in this sense that it nicely explains the observations. So I want to pause here. Well, actually, let me show you the results of the numerical simulations. So this is evidence from the observations that the simple analytics that I presented can explain the Kennicutt-Schmidt law. And here's now results from numerical simulations that support this simple understanding, and I think provide more insight into it. So all the simulations that I'm going to show you in this presentation implement the so-called fire physics, and I will return to fire in the context of cosmological simulations toward the end of my presentation. So on this slide, these are actually high-resolution simulations of isolated galaxies. And what that means, the fire physics, is that these are simulations in which we've implemented subgrid models that are intended to provide a good representation of how the real interstellar medium of galaxies behave. So we allow the gas to cool to tens of degrees Kelvin by a combination of atomic and molecular line cooling. That's because we want our simulations to be able to self-consistently form giant molecular clouds. we, in these calculations, allow the gas which is sufficiently dense to be converted into stars in the region where that gas is self-gravitating. And this is important. We approximate, following a star formation event, the energy and momentum return in the surrounding ISM from supernovae, photonization, stellar winds, and radiation pressure, following the proper time dependence for each one of these stellar feedback processes using star bursts. So these are images in the gas and in the star for what one of these simulated galaxies looks like. And at the bottom here, I'm showing you numerical experiments that show you how the simulated star formation rate in this model galaxy, as a function of time simulation, varies when different parameters of the calculation are changed. What you can see, if you focus first on the left-hand side, in which what is done is vary the details of how gas is converted into stars at the resolution scale. That is at very high densities, including the local star formation efficiency at these high densities, that basically the predicted star formation rate integrated over the galaxy as a function of time does not change on average. And that makes sense because in the simple analytic theory that I described, the star formation rate in a galaxy is set by a global vertical hydrostatic balance, and the theory did not refer at all to how stars got converted, how stars form out of gas in very small scales, deep inside molecular clouds. And so, in agreement with the simplified analytic theory, here the numerical simulations show that varying how that small scale conversion of gas into stars happens in detail actually doesn't affect the predicted star formation. On the other hand, as in the analytic theory, when we artificially vary the normalization of our stellar feedback energetics, we find that the galaxy integrated star formation rate varies nearly inversely proportionally with the strength of the feedback. So that's in agreement with the 1 over p star m star scaling of the analytic theory. So this is evidence, I think, that simplified global hydrostatic balance model for the Kinnear-Schmidt law is what's actually realized in these numerical simulations. And now I actually want to pause and ask if there are any questions, because what the rest of the presentation will be about is studying circumstances in which this nice equilibrium between gravity and stellar feedback is expected to actually break down.
So when you're doing this, you are off in terms of the star formation. How are you converting gas to stars?
Right. So so this is an unresolved process. So this is where the subgroup prescription comes in.
So you just say, like, once it hits a certain density, poof, it becomes a star.
Yeah. So in reality, so what we do is a little bit more sophisticated than that. And it is that in addition to have a minimum gas density, we check that the parcel of gas is locally self-gravitated. Because in principle, you could have a high-density cloud that has, a huge shear, in which case it's not self-gravitating, and so it should not collapse. But your intuition is correct. We basically turn a very high-density gas into stars at the prescribed rate. So that's what I call the local star formation efficiency.
So you require the gas to be a certain temperature?
Yes, that's basically done through the check of whether this is self-gravitating, because a high temperature would cause the gas not self-gravitating. And basically what these tests here on the left-hand side show is that if you vary by a factor of 10,000 the efficiency with which you turn the gas into stars at very high densities, that has zero impact whatsoever on the predicted galactic star formation rate. Okay, so the local star formation efficiency has no impact on the total amount of stars that end up forming in the galaxies. And the way to think about this is that basically galaxies form just as many stars as is necessary for them to remain in vertical hydrostatic balance. So the weight of the disk gas per unit area in the galactic disk basically in this model sets how many stars need to form in order for the feedback to exactly balance, at least in the time average sense. The graph.
The star formation efficiency here, that's number of stars formed per unit mass.
Per free fall time.
Per free.
Yeah.
Yeah. And okay, so the fact that it doesn't vary with the star formation efficiency, that's just because of the hydrostatic equilibrium. But that will make different predictions. So if you do vary the efficiency, that'll make different predictions for the disk scale height, I'm guessing.
So not the scale height, it does, it would make a difference. It would make different observational predictions for detailed ISM observations. For example, it would change, for example, the fraction of dense gas inside molecular clouds. You would anticipate.
So is the scale height also independent of these things?
It is independent. Now, the star formation efficiency that we're talking about here is deep inside molecular clouds. And basically, one of the reasons the value of this local star formation efficiency is able not to have an impact on galactic scales is that the local dynamical times deep inside GMCs are so much shorter because of the high densities of the global dynamical times of the galaxy that the gas can be converted into stars fast enough locally to respond to provide and produce and particle So I now want to move on to discuss limits in which this effective feedback regulation is anticipated to break down. And that includes places in the universe where the gravitational collapse because of high emit densities is going to be too fast for stellar feedback to respond in time. And related to this, in places in the universe where the total star formation rate is dominated by a small number of bright star-forming regions. And this is actually not independent from point number one, as I will explain, because these bright star-forming regions each tend to be in the limits number one here, the local dynamical times. And I'll argue that this applies both to local galactic nuclei as well as to entire high-redshift galaxies. Okay. And the way to think about this is that stellar feedback has a characteristic time scale. That's because stellar evolution has characteristic time scales. It takes a certain number of millions of years after a new stars are formed for them, in particular, to go supernovae. So this is the same plot that I showed before for momentum flux versus time since a burst of star formation. And for simple analytic estimates, the time scale that I want to focus on is the time scale for supernova feedback to output most of its momentum, and I'm focusing on supernova feedback for two reasons. The first is that it actually dominates the total time integrated momentum return in the interstellar medium over radiation, for example. And furthermore, supernova feedback continues significantly past the time when radiation dominates. So it has a longer characteristic time scale, so of the significant stellar feedback processes. And so the condition that the local freefall time becomes smaller than the characteristic time scale for stellar feedback to act will first become satisfied when the local freefall times become shorter than the time scale for supernova feedback to act, rather than for radiation to act. Now, in the main parts of local galaxies, like in a solar neighborhood, the mean densities in the interstellar medium are such that the freefall times in the ISM are somewhat longer than this characteristic time scale for supernova to act. And that is why this simple vertical hydrostatic balance theory for the Koenig-Schmidt law, I believe, works. Namely, as the gaseous disk begin its initial collapse, the supernovae start exploding fast enough that the momentum injection can actually respond to the onset of gravitational collapse and bring the disk into a quasi-steady, stable vertical balance. But there are places where the local dynamical times are so short that when gravitational collapse starts, it just proceeds too fast for the stellar feedback to have time to respond and puff up the disk back around its equilibrium value. And this is where I expect star formation to be substantially more bursty. And in particular, in the limit in which the local free fall times are extremely short, the gas can collapse actually too fast for even radiation to have the chance to prevent the runaway conversion of gas into stars, and so that can lead to regions in the universe where locally the star formation efficiency can be up to order unity rather than just a few percent like it is on galactic scales. Now, at the same time, after you form a bunch of stars, the feedback on the supernovae will continue for more than 20 million years, even if the gas has already been locally evacuated by other feedback processes like radiation, because the stars don't care whether there's still gas around. They continue to evolve, and eventually they will explode. And so this is why these regions can also lead to situations in which the stellar feedback overshoots the balance that I described earlier, and in this way can produce an explosive blowout of the gas locally. And so this is why in these short dynamical timescale regions, I anticipate that star formations will experience bursty cycles in which you can initially have a high local star formation efficiency per free fall time, then the gas blowout as the feedback overshoots, and in circumstances in which there's an external supply of gas to replenish the medium, like, for example, inflows of gas in the intergalactic medium, this sequence here can potentially okay, and then I will argue that this is actually what we expect in the center of local galaxies, as well as generically in galaxies at high redshift. And I'll support that by numerical simulations. Now, one of the points that I want to return to is the fact that star formation can also be bursty when it's dominated by a small number of star-forming regions. And that's because individual star-forming regions are generically in the limit that I described, in which the free fall time in the molecular cloud is shorter than the feedback timescale. And this is illustrated here in a set of numerical simulations that have exactly the same physics that I described earlier for the full galaxy simulation that I showed, but in which what we set up is a simple models for molecular clouds, which are overdense relative to the background stellar medium of galaxies. And basically in each one of those simulations that we've carried out, which cover a wide range of initial cloud parameters, what we find is that initially the star formation rate in these clouds increases roughly linearly with time as gravitational collapse proceeds, and then declines either as the gas has become exhausted by the star formation process itself, or as it's been expelled by the feedback. So individual star forming regions in general are expected to be well out of equilibrium and experience this kind of single star formation burst. Okay. So let me now focus on the centers of local galaxies. And here what I mean by galactic nuclei in this presentation is roughly the inner 100 parsecs of galaxies. And these are places where the free fall time at the mean density in interstellar medium becomes short, because one can show that for a disk which is marginally gravitationally stable as a cubic parameter of order unity, the free fall time at the mean density in the ISM is a constant fraction of the local orbital time, and for flat rotation curves, this orbital time tends to zero as values in the center of the galaxy tends to zero. And so this is a place where we expect the kind of bursty star-formation cycle that I just described. And this is going to be exacerbated because when you focus your observations on small apertures, you tend to capture a smaller number of bright star-forming regions, which, like I just explained, are generically in this limit where they turn the gas into stars in one main burst of stars. We've checked this behavior in numerical simulations. Again, the same physics that I described before. So these are images of the stellar and gaseous distribution in one of the simulations that we've run. And what is plotted in the pair of panels at the top and at the bottom is the total gas mass inside a given aperture. In this case, 100 parsec at the top and a full kiloparsec at the bottom, centered on the galactic nucleus. And in the panels in the bottom row, the corresponding integrated star formation rate in that aperture. And what you can see is that when you restrict your aperture to the inner 100 parsecs, as the analytic argument suggested, that the star formation rate versus time in these simulations of different curves here corresponding to different galaxy models is quite time dependent. And for certain periods of time, it actually drops to nearly zero. And that's because in these periods of time, the nucleus has actually been nearly completely evacuated of gas by overshooting stellar feedback. And just to contrast what we find in these galactic nuclei to what is found when you analyze the same simulation on a larger spatial scale, contrast these two panels at the top with the ones at the bottom here, in which in the inner 4 kiloparsecs of total gas mass is much more time steady, and the star formation rate correspondingly is significantly more constant. This is a numerical realization of these bursty star formation cycles in galactic. This, of course, has consequences for the expected Kennebec-Schmidt law if you were to measure it focused on galactic nuclei. And as you might expect from these choppy star formation rates here, the predicted scatter in the Kennebec-Schmidt law in these small apertures is much greater than what is observed when you average over entire galaxies. And you can see specifically how the Kennebec-Schmidt law in these simulations change from when you measure it in an aperture which is centered on the inner 100 parsecs versus the 4 central parsecs. There appears to be evidence that real galaxies experience bursty star formation in their nuclei. So this is observations by Rick Davies and his group using adaptive optics of the inner 10 to 100 parsecs of local Seyfert galaxies. And what they find generically in those local nuclei is that there's evidence for young stars in the spectrum, but actually very little typically ongoing star formation. And that comes from the anomalously low like a gamma emission that they typically find. And they argue that this is consistent with the recurrence timescale for bursty star formation in these nuclei of order 10 to 100 billion years, roughly in line with what we found in our numerical simulations. And in our own Milky Way, we observe so-called Fermi bubbles in the gamma ray sky, which, based on the observationally inferred expansion velocity and scale height, have a dynamical age of order 5 to 10 million years. And so a tantalizing possibility is that 5 to 10 million years ago, the Milky Way was a Seyfert galaxy, and it experienced its own burst of star formation and possibly also a black hole feedback that inflated these bubbles as we observed in our own Milky Way. So let me pause again and ask if there are questions about this concept of bursty star formation in galactic nuclei. The next step would be to argue that this behavior is expected to generically apply to entire galaxies at high redshift and explore the consequences of that. Yeah.
So you haven't talked about INF at this point. I'm assuming you have to convert to stars and supernovae, yada yada. So like,
Yes.
So this doesn't really depend upon the assumptions.
So
or
in
use
these
something
calculations, we have not varied the IMF as a standard Cooper IMF.
Okay.
If there is evolution or environmental dependence of the IMF, it would change these results a little bit quantitatively to the degree that the number of massive stars that you form relative to the number of low mass stars that you form affect the amount of feedback that you get from a certain mass form. But for all kind of the reasonable IMFs, including bottom heavy ones that have been claimed for the center of local elliptical, our results will be quantitatively affected by maybe tens of percents, but not qualitatively.
Right, that's not what I was looking for. So like, it doesn't matter, even if you had a spatially very high IMF, which I always forget if there's evidence for or not in the galaxy.
Yes.
It doesn't matter.
But I mean, I think it would affect some of the quantitative details, but not the kind of first order behavior that I'm emphasizing. Okay, so at high redshift galaxies, galaxies of the given mass were actually smaller than they are today. Quantitatively, observations suggest that, very roughly speaking, the half mass radius of galaxies is a constant fraction, about 2% of the radius of the parent dark matter halo. And this is actually consistent with the simplest theoretical models of disk formation, in which the specific angular momentum of baryonic disk is inherited from the parent dark matter halo. And because these disks at fixed mass become smaller and smaller as you go to high redshift, one can also show that the orbital periods in these galaxies become shorter and shorter at earlier times. And in fact, quantitatively, this is kind of a neat result. One can show that also for a disk which is marginally gravitationally stable, the free fall time in the intestinal medium, evaluated at its kind of mean density, is a constant fraction of the age of the universe at any redshift and only weakly dependent on galaxy. Okay, and of course the age of the universe tends to 0 as redshift tends to infinity. And so the implication is that as you go to high redshift, the ISM of galaxies tend to want to naturally collapse on a time scale which is ever shorter, and eventually becomes short enough that stellar feedback will have a hard time maintaining these disks in vertical hydrostatic balance, as I described earlier in my presentation. So this is a situation actually analogous to what happens locally in galactic nuclei. And quantitatively, I've attempted to estimate where this kind of transition should occur from steady star formation in the local universe to bursty star formation at high redshift. And I've done this by evaluating the free fall time in the ISM as a function of redshift for galaxies of different fixed stellar mass. It turns out that the stellar mass you assume here has a very weak impact on the calculation. And here the horizontal dashed line is this characteristic time scale for supernova feedback to light. And what you can see is that roughly below redshift of 1, galaxies evolve slow enough under the action of gravity that stellar feedback is expected to be able to respond effectively to runaway collapse. But that is roughly starts breaking down above redshift of 1 when the dynamical time scales in the disk become too short for that steady balance to be realized. And so the conclusion is that roughly speaking, at redshift greater than 1, I anticipate galaxies as a whole to become analogous to local galactic nuclei in terms of the bursty star formation cycles they are expected to exist. And like in galactic nuclei, these bursty star formation cycles will be enhanced by the fact that in high redshift galaxies, a lot of the star formation tends to happen in a relatively small number of bright star forming regions. And here, the way to understand this is that it's observed that as you go to high redshifts, because of the massive inflows of gas from the intergalactic medium, the gas mass fractions in galaxies become significantly higher. In particular, for Milky Way mass galaxies, the gas mass fractions in galaxies at redshift of 2 are about a factor of a few to 5 higher than they are in the Milky Way today. And the characteristic mass for the most massive star-forming regions in a galactic disk scales with the so-called TAMU mass of the disk. And that scales actually with the cubic power of the gas mass fraction. So this is why in these high redshift galaxies, we tend to observe star formation which is concentrated in a relatively small number of UV bright clumps, each of which is anticipated to experience kind of a peak of time-dependent star formation. Okay, so this is kind of the analog of small apertures in local galactic nuclei, typically encompassing only a small number of bright star formation. And as before, I want to now proceed with numerical simulations. So these are fire simulations with the same ISM, star formation, and stellar feedback model that I described before, but in this case with fully cosmological initial conditions. So what this shows is a formation of the Milky Way mass galaxies from the early universe to the present time. And what you see at the top is the gas in the simulation, and at the bottom the stars that emerge. And what you notice is that at high redshift, the gas distribution here is highly dynamic, and you'll notice in particular some powerful radial pulsations. So these powerful radial pulsations in the cool simulated gas are basically galactic winds that are driven by powerful bursts of star formation followed by energy injection from supernovae. And one generic feature of these high-resolution simulations of Milky Way-like galaxies is that there's a characteristic transition from this very bursty behavior of the stellar feedback at high redshift in a chaotic gaseous morphology to, at late time, a more well-altered disks, both in the gas and in the stars, that ultimately are reminiscent of local spiral galaxies. Okay, so this is just one example, but basically in every one of our cosmological simulation of a Milky Way mass galaxy, we find this behavior of essentially constantly exploding progenitors at high redshift, and roughly speaking, again, the emergence of a well-altered galactic disk below redshift of 1. We have samples of dozens of such zoom-in simulations now, so one of the big things we've been doing over the past few years is validate them by comparison with a variety of observations. So this is not the focus of my presentation today, but I want to show you some basic comparisons of these numerical cosmological simulations with observations to convince you that they are useful tools to study galaxy evolution. So each one of the colored points on the left here shows the ratio of, shows the stellar mass as a function of parent dark matter halo mass at redshift of 0. And basically the observation, or the observational inference from so-called abundance matching are indicated by the cyan and magenta curves here. And so the takeaway message here is that basically these simulations produce galaxies that have reasonably accurate stellar masses when compared to observations, and this is significant because in these simulations this results from the action of known stellar feedback processes and do not require any fine-tuning of the model, which is furthermore a significant achievement because at low stellar masses, stellar feedback actually suppresses stellar masses in galaxies by a factor of nearly 10,000 relative to how many stars these galaxies would form absent feedback. And on the right-hand side, I'm showing essentially how these simulations also produce galaxies at the high metallicity versus stellar mass. So I want to now return to this bursty behavior at high redshift that you could see in the video. So this is a quantification of it for the same simulated galaxy as in the animation. What is shown in black here is the star formation rate versus time at high redshift, from redshift of 4.5 to redshift of 2. And you can see that a lot of the star formation occurs in these powerful bursts, well out of time-steady equilibrium. And typically, these bursts of star formation in black are followed by bursts of outflow in gas to a quarter of the virial radius, traced by the dashed red curves here. And these peaks in the dashed red curve is basically the pulsations you could see in the cool gas in simulation. And that redshift, the galaxy morphology is very clear. And what's now shown on the right-hand side is quantitative measurements from exactly the same simulation, but in this case between a redshift of 0.5 and a redshift of 0, so at late time. What you can see is that the star formation rate at late time in the same simulation has become much more time steady and achieved this kind of balance that we saw in the first part of my presentation. And that empirically in our simulation tends to correspond with the emergence of much more well-ordered rotating galactic. And so my proposal here is that this characteristic transition from bursty star formation at high redshift to more time-steady star formation at low redshift can be understood to first order by this transition in the hierarchy of timescales from the limit at high redshift where the free fall times in the disk are too short for feedback to respond effectively to the opposite limit in the local universe where stellar feedback can in fact maintain disk in a state of what they call hydrostatic balance. And that is further helped by the fact that galaxies transition from having quite high gas fractions at high redshift to more modest ones at low redshift, which reduces the characteristic size of star forming regions and allow star formation to be more evenly distributed throughout galaxies. And for the next couple minutes, this is the last topic of my presentation now. So these are preliminary simulations like the ones that I just showed you, but in which we are now also tracking the growth of supermassive black holes. So these are the first 5 cosmological simulations with supermassive black holes in them. Supermassive black holes require approximations in the way that they are modeled in this kind of simulation, because we don't actually resolve the formation. So what we do in this type of calculation is that when galaxies are first resolved in a simulation at high redshift, we by hand put in black holes and then prescribe seed masses. And what we do is we track how the black hole moves in the simulation, and tied to the surrounding gas, we track how much gas the supermassive black holes are predicted to have accrete from the surrounding galaxy, i.e. how supermassive black holes grow with time. So this is an animation from one of these simulations, which show you different physical scales, from large-scale structure to centered onto the galaxy as a whole, to centered around the nucleus, the inner two proper kiloparsec in this case. And on this animation, each one of the black dots here is one supermassive black hole. Now, yeah?
We don't see that. I mean,
Don't see
you
what?
say the supermassive black holes, you were going on the issue too. And so,
Yeah.
what evidence do we have for,
That there are supermassive black holes?
well, that they do exist, I have no doubt, but that we don't
Yes.
have that many and they're always really small volume.
So I think that's a fair comment. I guess that's something that in principle we will want to compare. We would want to compare the simulations to the observations to assess to what degree these models are accurate. So right now we don't know. So we are making predictions, and we will be interested in testing them with observations. But as you see, a lot of these black holes here that pop up are not very massive, so they could easily be missed in observations. Now the point that I want to emphasize here is that if you focus on the right-hand side, that's the part of the simulation that's centered around the supermassive black holes near the center of the galaxy, and that you see that at early time, the gas distribution is extremely choppy, and that's because the gas in these galactic nuclei, because of the local dynamical time scales, actually move quite fast. In fact, faster than the time interval between simulation snapshots that we write to this. So that's why in the movie the evolution is quite sharp. But one thing which is a prediction of these calculations is that the nucleus at early time tend to be very frequently depleted of gas, and that is in large part because of these feedback events. But that as time progresses, a well-ordered galactic disk eventually emerges with a more time steady supply of gas can in principle fuel the black hole. Okay, and here's a quantitative representative example of how the main supermassive black hole at the center of the main galaxy that's tracked in one of these simulations evolves with time. So the top row here shows the mass of the supermassive black hole as a function of time from very high redshift to redshift somewhat below 2 here. As you can see it growing with time. Just underneath it is the black hole mass accretion rate versus time. So you can see that that's very sharply at early time, and eventually picks up somewhat. This is again the black hole accretion rate versus time, but normalized to the Eddington accretion rate of the black holes. That's a measure of the Eddington ratio of the accreting supermassive black holes. And these are diagnostic curves that actually track the amount of baryons right around the supermassive black hole on scales that are resolved in non-numerical simulations. And basically what you can see is that in this representative example, at early time, the supermassive black hole is growing quite slowly, and it typically reaches a point where it accelerates in its growth. And what we're finding is that the point where the black hole growth accelerates significantly generally corresponds to the time in which, in the simulation, the supply of gas in the simulated nucleus becomes more time steady. And that is correlated with the emergence of well-ordered galactic disk, which can provide a more continuous supply of gas in the inner. And a consequence of that for the predicted relationship between supermassive black hole mass and, in this case, the bulge mass of galaxies has this kind of behavior in time. So these are in color here, essentially time trajectories of how supermassive black holes in the simulations move in this plane from the time we see them in the early universe to the end of the numerical simulations. And what you can see is that the generic behavior is that at early time, black holes grow relatively slowly because they often don't find gas right around them to accrete because of the stellar feedback that constantly depletes galaxies, and in particular the inner parts of gas from which they can feed. And then you have this kink-like behavior that, as I mentioned, corresponds in our analysis to when galaxies start developing a more stable galactic disk, at which point black holes start growing until they reach something like the observed local scaling relation, at which point they tend to remain on that scaling relation. And the reason they tend to remain on the scaling relation once they reach it is that in our model for how supermassive black holes grow, both the black hole mass accretion rate and the star formation rate in the nuclei are tied to the amount of gas in the galactic nucleus. So they tend to grow in parallel once black holes have reached the scaling relation. So this is kind of a brand new line of work for us. So we have a lot more to do to understand exactly what sets the onset of rapid black hole growth, whether stellar mass or redshift, for example, is the best determinant, and also testing whether the predictions of these models for supermassive black hole growth and aging activity are consistent with observations. So I encourage you to stay tuned for more results on black holes over the next few years. And this is actually my last science slide. I'll be happy to take questions.